In this video, we're going to focus on solving physics problems associated with open tube manometers. So the open tube manometer shown below contains liquid mercury, and we're given the density of mercury. What is the pressure of the gas in the bulb? So this is the reference level. And what you need to know is that the downward pressure exerted on the left side of the tube has to be equal to the downward pressure on the right side of the tube. In order for the system to remain in equilibrium, the forces on the left side has to equal the downward forces on the right side in order for it to be balanced. And pressure is force over area. So if the area is constant, pressure and force are directly related. On the left side, the only pressure that pushes down on the fluid is the pressure of the gas. On the right side, this side is open to the atmosphere. And so the pressure of the atmosphere pushes down on the fluid, and also the weight of the fluid above the reference level also exerts a force. And the fluid is liquid mercury, so I'm going to use the chemical symbol Hg to represent mercury. So on the left side, the only pressure that we have is the pressure of the gas. On the right side, we have the pressure of the atmosphere plus the pressure of liquid mercury. Now the pressure of a fluid, or the pressure due to the weight of a fluid, is always equal to the density of the fluid times the gravitational acceleration times the height of the fluid. And so that's going to help us to calculate the pressure of the gas in the bulb. Now the only thing that we're missing is the atmospheric pressure, which was not given to us in this problem. So if it's not given to you, always assume that the elevation is at sea level. And at that elevation, the atmospheric pressure is 101,325 pascals. And then rho is the density of the mercury, which is 13,600. G is 9.8. And the height, which is in centimeters, so we need to convert that to meters. So 60 divided by 100 is 0.6 meters. So if you type this whole thing in, you should get a pressure of 181,293 pascals. So that's the pressure of the gas in the bulb. Now what about the gauge pressure? The gauge pressure is the difference between the absolute pressure, which is basically the pressure of the gas, and the atmospheric pressure. So that's the gauge pressure. The gauge pressure is basically the pressure due to the weight of the mercury column in this example. So the quantity pGh, or rho gh, that is the gauge pressure. So if we subtract 181,293 pascals minus 101,325, that's going to be 79,968 pascals. That does not look like an A. So that's the gauge pressure in this example. It's the pressure that is above the atmospheric pressure. Number 2, we have the same exact problem, however there's only one small difference, and that's the way the fluid is distributed. So go ahead and calculate the pressure of the gas in the bulb and also the gauge pressure. So let's say this is the reference level, and keep in mind the pressure exerted on the left side, the downward pressure exerted on the left side of the tube, is equal to the downward pressure exerted on the right side of the tube. So on the right side, we only have the pressure of the atmosphere. On the left side, we have the pressure of the gas, and also notice that we have mercury above the reference level on the left side. So the weight of the mercury above the reference level is also going to exert a downward force, and thus a downward pressure on the left side. So on the left side, we have the pressure due to the gas and the pressure due to the weight of mercury. which is basically the gauge pressure. And that's going to equal the atmospheric pressure. So this time, the pressure of the gas is the difference between the atmospheric pressure and the gauge pressure, or the pressure due to the weight of the mercury column. So just like before, the atmospheric pressure is going to be 101,325 pascals. And then this is equal to pGh, or ρgh. The density of mercury is going to be 13,600. The G is going to be 9.8. And the height difference, which is 40 centimeters, divide that by 100, and that's 0.4 meters. So the pressure of the gas is pretty low. It's 48,013 pascals. Because the pressure of the gas in this problem is less than the atmospheric pressure, that means that the gauge pressure is going to be negative. To calculate the negative gauge pressure, we need to take the difference between the pressure of the gas and the pressure of the atmosphere. So the pressure of the gas is 48,013 pascals, and the pressure of the atmosphere is 101,325. And so that's going to be negative 53,312 pascals. Now, you need to be careful when using this equation. Let me just erase a few things. The gauge pressure can be found using this equation, ρgh. However, you need to know when the height is positive and when the height is negative. Because if you just plug in 13,600 times 9.8 times the height difference of 0.4 meters, this will give you the same magnitude, but not with the appropriate sign. So be careful when calculating the gauge pressure using this formula. You're going to get the right number, but if the sign is important, you may want to do it this way. So remember, in order to calculate the gauge pressure, you're comparing the pressure of something important, in this case like the gas, with respect to the atmospheric pressure. So let me just give you some examples. So let's say the atmospheric pressure is a constant 100,000 pascals, just to keep life simple. So this is slightly above an elevation of sea level. So we're just above sea level, but not exactly there. So let's say the pressure of the gas is 70,000 pascals. So notice that the gas pressure is less than the atmospheric pressure. So the gauge pressure is going to be negative. It's negative 30,000. So anytime the pressure of something is less than the atmospheric pressure, it's going to produce a negative gauge pressure. Now let's say if the pressure of the gas is above the atmospheric pressure, let's say it's 150,000. So this is going to lead to a positive gauge pressure of 50,000. So if you need to find a gauge pressure, compare the pressure of the substance to the atmospheric pressure. If it's above the atmospheric pressure, you have a positive gauge pressure. If it's below the atmospheric pressure, then that's going to lead to a negative gauge pressure. Number 3. The U-tube manometer shown below is filled with a fluid of unknown density. The height difference between the two columns is 1.3 meters. So this is 1.3 meters. If the pressure of the gas in the bulb is 92,000 pascals and the other side is open to the air at sea level, what is the density of the unknown fluid? So here's our reference level. Now keep in mind the pressure exerted on the left side is equal to the downward pressure exerted on the right side. So on the left side, it's open to the atmosphere, so that's going to be the atmospheric pressure. On the right side, we have the pressure of the gas pushing down on the fluid, and also notice that we have some fluid above the reference level, so the weight of that fluid is also going to push down on the right side. So I'm going to write PF for the pressure of that fluid. So on the left side, we only have the atmospheric pressure pushing down, and on the right side, we have the pressure of the gas and the pressure of the fluid above the reference level. Now let's subtract both sides by the gas pressure. So the atmospheric pressure minus the gas pressure is going to be equal to the pressure exerted by the fluid above the reference level. Now the atmospheric pressure at sea level is 101,325 pascals. And the gas pressure, that's 92,000 pascals. And the pressure of the fluid, which is basically the gauge pressure, that's going to be the density of the fluid times G times H. Now 101,325 minus 92,000, that's going to give us a positive value of 9,325 pascals. And so that's going to be equal to the density times the gravitational acceleration, which is 9.8, and the height of the column, or the height difference between the two columns, is 1.3 meters. So let's multiply 9.8 times 1.3 first. So on the right side, we have 12.74 times the density, and that's equal to 9325. Now let's take 9325 and divide it by 12.74. So the density of the fluid is equal to 732 kilograms per cubic meter. And so that's the answer in this problem.